nice to be here. Thanks for the invitation. This is the first time I'm giving a talk in this venue. So I'm an aerospace engineer. So like it goes, if you wear red glasses, you see the world red. If you wear blue glasses, you will see the world as blue. And if you wear yellow glasses, you will see the world as yellow. So I am a jet engineer, aerospace engineer, looking at flames and jet engines and so on. So everywhere I look, that's what I see, and that's what I did when I looked at coronavirus propagation and so on. I guess there's some truth to this saying. So before I proceed, I want to acknowledge my postdocs, Induja Pavitran and Ankan Banerjee, who did all the work. And let's go get into it. So we had this ferocious COVID wave last year this time. In fact, the students also felt sick at that time. So we saw that in the first wave, it took about 110 days to get to 98,000 cases per day. And then the delta hit us. It reached the same, it breached the 100,000 mark, 1 lakh mark in about half the time, 62 days. And then subsequently, it just flared up like hell. So it went to like 4,16,000 phenomenally fast in very, very short time that nobody imagined it would be so fast because country had declared victory over COVID and all that time. And then this came. And then the virus wreaked havoc, and we were not prepared for such a sudden increase in COVID cases, and there was no oxygen and so on, and lots of problems, and I think I don't have to say it. In fact, my entire lab fell sick. 4 of them were in ICUs. Luckily, all came out fine, fortunately. So we know that population growth of biological system has been modeled as exponential function, exponential growth, and it's a very standard model. And generally, there is a feeling that exponential growth in the number of infections is like the defining feature of the spread of the pandemic. And then the question comes then, if it was exponential is a fast function, but e power t goes to infinity at infinite time. And so given what we saw in the first phase, we didn't anticipate such a steep rise, and so how did such a rapid rise of infections happen for the delta wave? That is the question that I wanted to ask. In fact, I was thinking all these things at that time. So I was seeing these curves at that time as this was picking up, and we were thinking that something disaster was going to happen, but then we couldn't do anything about it because everyone fell sick, unfortunately. It sounds very dramatic, but it's truth, including my students, actually postdocs. They were students then. So the question is, by looking at this, can we get any precursory signals a priori? Then the government could do something really messy is going to happen, and 4 times more than first year what happened, and then okay, we could put in restriction, because by the time we realized anything happened, it had become too much. So let's look at this function e power x, exponential function. It's the most famous function perhaps, or one of the most famous. And this is how it looks like. But if you plot this in a semi-log plot, so one of the axes is log and the other is straight, so this is log, it will look like a straight line. So exponential growth will appear as a straight line in a semi-log plot. So this is maths 101 or something. So if you look at many of the COVID waves, for example, here I have plotted cases of UK 3rd wave, Germany 4th wave, South Africa 1st wave, USA 1st wave, and we are looking at 7-day average of daily infections. And why 7-day average? Because then Saturday, Sunday, maybe not much testing and so on, so to wipe out these fluctuations. And we see that exponential growth of infections has been indeed observed in many ways. But the question is that the only possibility? Is it always exponential? So we look at some of the, including our 2nd wave in India, 3rd wave in US, 5th wave in Japan, and Italy 2nd wave. We see that the curve in the semi-log plot is concave upwards. This is a sign that the function is growing faster than the exponential function. Okay, so it's called hyper exponential. Some people use it. I think fluid mechanics people use it, the term super exponential, but mathematicians seem to call it hyper exponential. I am neither of this, but I think I just stick with this term. And so this is faster than exponential. So in contrast to the exponential case, which we saw in the earlier cases that I've showed, we observe faster than exponential growth during this extreme COVID-19 waves. So is there exponential and faster than exponential? Can there be slower than exponential? Yes. In fact, but before one more thing, the growth of human population is known to be hyper exponential or super exponential, and this is a well established and accepted thing actually. A lot of work on this. Now, if will we get slower than exponential, which is concave downwards? Yes. The first waves in many of the countries, UK, Brazil, even India and Mexico, they actually were slower than exponential, because when the coronavirus came, people were really scared and there were severe lockdown measures and so on. So that's what happened. And then, so we actually see both exponential, slower than exponential, and faster than exponential. And this is the one that wreaked havoc in many countries. Okay. Now, the typical model of population growth says that 1 over I dA by dt, that's the relative growth rate, is a constant. Okay, that's the that's the workhorse model. Is there any way we can generalize it? So we say that dt is k I power m. Now that way m equal to 1 is the classical exponential case. Now if m is greater than 1, then we will get this hyper exponential solution, and if m is less than 1, you will get the slower than exponential growth. So the existing exponential description is a special case, and we can have a general case like this, and exponential function is just one specific solution to this model, or to this growth equation. Now m is greater than 1, that's when you get this power law kind of thing, which can blow up to infinity for a finite critical time. So we don't have to go to infinite time to get infinity. You can get infinity at a finite time, and that's called this is what you mathematician would say singularity there. So at a t critical, the solution can blow out, and you can blow up, and you can get unbounded growth in, and this would be called finite time singularity, and where this happens is the critical time. So exponential growth of infection has a constant growth rate and constant doubling time, whereas the doubling time is not constant for hyperexponential growth. You actually, the doubling time keeps progressively decreasing, and eventually there will be it will give progressively getting smaller and smaller, and eventually you will get infinite number of doublings within a finite time, and then the solution will blow up. So that is the problem with hyperexponential curve, and this leads to a finite time singularity. And if you look at the newspapers, there were lots of reports about doubling time coming down, and doubling time came as low as, I don't know, 4.5 days to 5 days for Delta wave, and later on for Omicron they said came down as slow as 3 days and so on. I'm not an expert, I don't know anything about these things, but this is like aerospace engineers' analysis of the situation. But it is a faster than exponential growth, which really was, it was so rapid that it wreaked havoc, and had anyone known this, they would have put much more stricter regulations and so on to probably hamper the impact of this COVID wave. So how do you, so instead of fitting, so normally they would fit exponential curves, and at different parts of the growth you will fit different exponential with varying constants, but instead for the entire curve you can fit a hyperexponential curve. I will not go into the details of that, but you can actually fit a power law, and the solution is a power law, and these are for certain particular cases. Now a single hyperexponential power law can allow us to characterize the growth of COVID-19 waves better, rather than the piecewise exponential that is used to fit, because as time progresses, the wave picks up, the doubling rate is coming down and the growth rate is getting faster. Instead, just one solution would work for the entire thing. And we have looked at many data, it's all available in public. I think till Delta it was okay, but except now nobody is testing much. So, but in all the reported cases, whenever there was an extreme case, we actually did see that these are hyper exponential curves and not really exponential. There are standard tests for these things. Now, if you look carefully, there are fluctuations around this hyper exponential curve, and we should not dismiss this as just noise or something like that. Instead, these fluctuations can be modeled as what is called log periodic oscillations. So what is log periodic oscillations? So this is a power law, and if I modulate with a cosine, which is actually going to, instead of cos x, we say cos log of x. So that means the periodicity will accelerate as you, if there is a time, and as you progress towards this critical time, the oscillation will get faster and faster. So this would be called log periodic oscillation, or there is a way to model such accelerating oscillations that is called log periodic oscillations. So if we look at number of infections versus time, it is hard to see, but if you look at the change every day growth rate, you can see these log periodic oscillations very nicely, because here the rise is too sharp that you can't really, it is hard to make out. And now you can look at the periodogram, and you do a periodogram where you are looking at the frequency in terms of the log periodic angular frequency. So we have, it is periodic in log time, so you can get a log periodic angular frequency, and we see a significant power on frequency. A peak in the periodogram is indicative of log periodic oscillations. So there are indeed these log periodic oscillations, and log periodic oscillations are precede finite time singularity, but then you do not never go to infinity, because once the wave picks up very rapidly, of course eventually people are going to get sick, so they are going to isolate, people are going to get immunity because they already fell sick, and government is going to put lockdown. So that is what happened, and when that happens, eventually the virus will run out of people, and then it will peak and fall down. But in the initial steep rise, it is a hyper exponential, which is why it is so steep. Now just only equation I have here. So if you we can think of the exponential the cosine as real part of exponential. So if you do that, we can write this this x power alpha times cos of omega log x, is the log periodic power law, that can be written as like a power law with a complex exponent. So it is very simple algebra. So now the question comes, it is intuitive for me to see, if I give virus to 2 people and each of them give to 2 other people and they give to 2 other people, then you should get exponential curve. So why is that you are getting hyper exponential? So the thing is that doubling time is, so there is an example where I am giving 2, you can construct an example with each person giving it to 3 or 4, whatever, and the doubling time will keep coming down, because as the virus mutates, as it spreads or inside the body itself, the one which spreads faster is favored. So as a result, the doubling time comes down, but we are sampling at constant intervals. So which is why it looks like each person is suddenly giving to more and more people, but it is actually, if you look at the levels, it is actually the same everywhere, it will be 2, but because it is getting crushed due to this finite time singularity, that is why the doubling time comes down, and it seems like the R0 value increases. So catastrophes are there in various fields. We wish there were no catastrophes. They happen in a wide variety of systems, they happen in real life, and there is, if you look at catastrophes across the systems, it seems like there is a general way in which every system approach catastrophe, and there are a lot of similarities in this manner in which systems approach catastrophe. So I am looking at the engine, so look at a combustion system, and I want to look at a specific problem called flame blowout. So flame should be inside the engine, and then you get power in the engine and thrust in the engine and so on, but the flame can get progress too fast and actually come out of the engine. This is the famous SR-71 Blackbird. Flame has come out, and the flame will come and stand outside the engine. That means inside the engine there is no flame, there is no thrust. This is a disaster, especially in a combat situation, because then you have to come down several kilometers down to relight, and then by then you are shot. Okay, so we never want to have this. So it will be good to know if in advance where you can get such a early warning or something. But blowout is a big problem. To us it is a catastrophe for an engineer. So in fact there is a lot of similarity between the blowout and coronavirus spread. So if you look at the amplitude of the fluctuation, flame is a turbulent flame, they are accompanied by sound. So if you look at the amplitude of the waves, you will see that there is a hyper exponential growth, and then at the end, as it picks up, it just flame is out, and then it collapses. And you also see this log periodic oscillation. So, and it's very similar to corona actually. You also see a rapid drop of doubling time and leading up to finite time singularity. Here you can see the flame just at the singularity, flame at the criticality, at the critical time the flame just blows out. Log periodic oscillations precedes flame blowout, and you can again do the same test with the long periodogram, and you can get significant power in some frequencies, and there is indeed log periodic oscillations. And blowout, just as virus, it spreads from one person to another person and then go on. Here what happens when a flame blows out, there are small flame holes, and these holes get the lot of holes coming, and then they merge together and they become a bigger and bigger hole, and then eventually entire thing is a hole and the flame goes out. That is the actual mechanism. So blowout of is the extinction of flames by formation of global flame holes. So the number of frequency and extinction and reignition events increase as the system approaches blowout. So during blowout, the collective behavior of local flame holes leads to the formation of large flame holes that ultimately results in blowout. So each extinction is part of a precursory sequence of even larger event with more local flame holes during such progression. So something happens and the same thing is reinforced and get bigger and bigger and bigger. So this is a movie, so you can see a small hole coming here. This is far away from the blowout, and you see this hole come, and then you can see eventually the lot of holes merge together and become a big hole. So this is actually a mechanism. There is a hierarchical system just like virus spread, and that's what gives this kind of hyper exponential behavior. And you can actually, as an engineer, we're always interested in prediction, so we want to get early warning for this, and then can you look at the sound signal and know somewhere here that we are going towards blowout, then we can take corrective action. So there's automatic algorithm we have patented and developed and so on. So the hierarchical systems underlying the precursory events were used to predict the corresponding critical phenomena. Here the blowout is a critical phenomena. So several phenomena such as stock markets, crash and earthquakes are all found to be preceded by small scale precursory events. And large earthquakes and stock market crashes occur as a result of scaling up a process of its earlier precursory events. This is actually a picture from Didier Sornet. He is studying the rupture of a rocket combustion chamber, the shell exploding, and you can see this kind of hyper exponential growth and then log periodic oscillations. And this is growth of human population, this hyper exponential curve, and people claim that there is a finite time singularity in 2030 something, and of course it won't blow up to infinity, but maybe some wars will happen or something. So, but anyway, these features are used to predict ruptures in engines, population growth, earthquakes, epileptic seizures, etc. So the dynamics of complex system exhibit generic features on approaching a critical phenomena regardless of the governing physical phenomena. So because there is nothing common between many of these things, but there is common features. So we see that although flame blowout in a jet engine, which is a completely engineering system, and corona, which is a biological system attacking another biological system, we see very similar features. So in summary, we saw extreme COVID-19 waves exhibit hyper exponential growth and log periodicity close to a critical point, and flame blowout is also preceded by hyper exponentially growing low amplitude oscillations decorated with log periodic oscillations, and log periodic power law model can be used to predict the critical points. So I want to thank my students. This is Induja, who did most of the work, and this is Ankan, and thank you.
Well within the time.
Thank you.
Thank you.
See, in chemistry and physics, fundamental physics, there is a distribution called Planck's distribution. E is equal to hv distribution. You are familiar.
I studied in first year BTech.
Most of your talk is about Stefan's function. It's due to the power of 4 law upward.
Okay.
Planck's distribution expects it should go down how?
Okay.
So you have mentioned somewhere later period there. Do you have a model where we can actually, where can you reach the peak and then come down? Because the coming down you have not got much.
No. Yes, I understood. Yeah.
You have said catastrophe and all that.
Yeah.
I followed it.
So I mean, at the moment, once it gets the peak, it really blows up.
Yeah.
Just after that, but I don't have.
How it is going down?
Yeah, I have not.
Where is the function there?
Yeah, that's the next thing to look at. Yeah, thank you. I don't have answer. Yes.
I have a short question about this oscillation preceding the divergence.
Yes, sir.
In the case of COVID, what is the meaning of that period? It looks like 1 week.
It keeps coming down, sir. So,
Now, at the beginning, it's about because you have omega logs.
yeah.
So omega looks like a week. So is there any significance?
Yeah, there is a significance actually. I don't know what a week means or something, but it is because of the discrete scale invariance. So normally power law happens for generally scale invariance, but here because of the hierarchical nature, because one human, I give it to certain number of people, integer number of people, and then I give it to 3 people, they give it to, each of them give it to 3 other people. So it's a scale invariance worked for, not for any general lambda x, but lambda 1, lambda 2, lambda 3, etc., where they are lambda squared, lambda 3. So this is related to that. So and the same in my flame spread, because 2 holes merge, to make a big hole, and another 2 holes merge to make a big hole, and then 4 of them merge. Of course, there will be inhomogeneity, but there is some underlying deep physics, I think, related to discrete scale invariance. I didn't want to get into that.
Last but one question.
Yeah, thank you, Sujith, for the very interesting presentation.
Thank you.
I was curious whether this hyper exponential can become sub exponential due to mutation of some variants, or you are assuming all variants have similar growth rate.
I really know nothing about virus, but from what I read in some papers and spoken to people, generally it seems, in general, the faster spreading ones are favored, and that is the reason. But it could be, there could be other things. Every wave is not this, so I am trying to give explanation for this very sharp rise.
The kinetics varies with also the strain.
Definitely, definitely. So I completely agree. But I am talking about if there is hyper exponential growth, what is happening?
So one quick question that I have is that when we look at these peaks,
Yes, sir.
if you don't intervene, it will go to a certain peak, and then, you know, like you said, finite time singularity is going to happen. But inevitably for these kinds of epidemics and other kinds of things, there is human intervention.
Absolutely.
That actually changes what you expect theoretically, right?
Absolutely.
So prediction is good, but prediction will also lead to interventions, and then it will not allow you to...
Absolutely, sir.
Yeah.
No, also just to add, even if you don't intervene, it will stop, because virus will run out of people. Because the herd immunity. Yeah, herd immunity.
Okay, just one
Reduce the higher signature of the particles.
Huh?
How can we reduce the higher signature?
Oh, I have no idea, sir. I don't deal with that. I mean, really. I mean, I have some answers, but I am not a professional answer. Maybe we can talk in the sidelines. It deals with the electromagnetic scattering cross-section, but I really am not knowing seriously about it.
So that was a real wonderful talk. Let us thank the speaker once again.
I think there were a lot more questions, so I would be very happy to talk to you during the day. Thank you.